I think we should now start to investigate and analyze a number of analog circuits that can be used for different purposes. Circuits that have the operational amplifier as its main component. And I think we can start with the inverting amplifier circuit, and then continue with discussing the common mode and differential mode signals. And this is important concepts to understand for the transfer and amplification of sensor signals. The difference amplifier used to measure differential mode signals. The instrument amplifier, the summing amplifier, charge amplifier, and in the end also analog circuits that can perform derivation and integration. We start with the inverting amplifier, and this is how the circuit looks like. The operational amplifier as the main component and two additional resistors as the passive feedback network. The input voltage and the output voltage, and the task is now that we should compute the relation for the voltage amplification, the output voltage divided by the input voltage. But first we can say that you can approximate this operational amplifier with an ideal model of an operational amplifier if you know that the raw voltage amplification of the operational amplifier is, let's say for a rule of thumb, maybe like 50 times higher than the amplification that you aim for in your circuits. And definitely if it's maybe like 100 times higher than the amplification that you aim for in your circuits. But the raw amplification of the operational amplifier should be high enough, in order to approximate the amplification as infinite and apply this ideal model. And we can assume that the input voltage over the input terminal are zero. If we at the same time can assume an infinite amplifier model. Let's say that you are powering up the circuit board with a few voltage, maybe like 10 or 12 voltage. So 12 voltage is the maximum peak output voltage. And then of course if you have like thousands or 10,000 times of amplification, or even more, infinite amplification of the operational amplifier, then the voltage here on the input terminal consequently will be very, very, very low. So that's why you can say that you can assume it to be zero. And this has some nice consequences. We can assume that the input terminal here, the input voltage terminal here on the amplifier that is not connected to the ground, acts as a virtual ground, since the other terminal here is connected to the ground, and we have said that the voltage between those two terminals are equal to zero. Then you can also assume that this terminal is acting as a ground, in this case a virtual ground. It is virtual even though it is not like connected directly to the ground. It has zero potential. So let's continue with the development of the equations for the circuit amplification. If you look at the current law of Kirchhoff on this node, assuming that according to the ideal operational amplifier model, the input current on the terminals to the amplifier is zero, then of course the current I1 and I2 must be equal, and you can denote it as I. And then we apply the voltage law of Kirchhoff on this circuit, and we say that U in minus the voltage drop over the resistor is equal to zero, since the potential on this node is zero. It's a virtual ground point. Then we can compute the current I is equal to U in divided by R1. That is the first basic equation that we have here. And then we apply the voltage law of Kirchhoff in this direction. So U out plus the voltage drop over R2, I times R2 is equal to 0, because then you ended up at this potential of 0 here on this node. And we can again compute the current I, since I1 and I2 are identical, it is equal according to the first equation. And now we are able to combine equation 1 and 2. On two different sides, we have U in divided by R1 and U out divided by R2, and this minus sign. And now we can rearrange so that we get the U out divided by U in, which is the voltage amplification of the circuits, is equal to minus R2 divided by R in. And then again, the voltage amplification of the circuit is determined by this external resistor network, the feedback network. We can alternatively describe it in the unit of decibel, and since we are comparing the voltage here, then we are using the factor of 20 and adding the comment of 180 degrees phase shift due to this minus sign. A differential mode signal is a signal that you are measuring between two wires that are used to transfer a sensor signal, for instance. A common mode signal, that signal contributes the same on both wires. So you compute the mean value on the voltages that you can measure on both these terminals with respect to the ground. That is a very short introduction. But let's have a look to this presentation on the slide. So this is the signal that comes from the sensor that has a differential mode output. And it ends up here on the terminals denoted by VA and VB. And you have the ground potential equal to 0. And then we can say that the voltage that we can measure on VA with respect to ground is the common mode signal, SCM, plus the differential mode signal divided by 2, SDM divided by 2. And the same is for the voltage VB, potential VB with respect to the ground. The common mode signal SCM, but now minus the differential mode signal SDM divided by 2. And then when we want to separate and measure the differential mode signal and the common mode signal separately, then we can start with the common mode signal. We compute it as the mean value of the potential VA and VB that we can measure on both of these terminals with respect to the ground. Then the result will be the common mode signal. On the other hand, if we measure the difference VA minus VB, then you will have the differential mode signal. And that is usually the kind of signal that we are interested in, that are stemming from the source, the sensor. And a good way of measuring the differential mode signal is by connecting a difference amplifier circuit that are based on the operational amplifier. As we can see here in this circuit diagram, it's an operational amplifier with the additional 4 resistors in the feedback network. And you apply now 2 voltages, U1, U2, and you have the output voltage U out. And the task now is to analyze the circuit and see what kind of relation and how will the expression look like for the output voltage with respect to U1 and U2. I've already given you the indication that you will have the difference of U2 and U1 as the output. But let's take this analysis from the beginning. So we can start with denoting the potential, voltage potential with respect to the ground. At this point we denoted VI. That is the voltage division over R2 and R3 with the input voltage U2. That is the first equation. And then we apply the Kirchhoff's voltage law on this circuit from U1 down to the potential of 0. So U1 minus the potential drop over R1 and minus this potential VI. And we end up in the expression for the current I as equation number 2. And we continue with the Kirchhoff's voltage law, going from the output voltage over the feedback resistor and back to this VI. So U out plus the voltage drop over R4 and minus this potential VI is equal to 0. And we again now solve this equation for the current I. And now you see if we have equation 2 and 3 both expressing I, the current, then we can combine these two equations and we can try to solve for the output voltage U out. We do that in a number of steps. Now we have U out on the left side and we need to eliminate for R1, and we have the expression for U out, but this expression still contains VI, which we need to eliminate. So we'll make a substitution from equation 1 in for VI in this equation number 4. And then we end up at a result that is pretty much expressing the output voltage as dependent on U2 and U1, but also of course then dependent on a number of resistors, these 4 resistors that we have here in the circuit. We continue with this result on the next slide. It's the same as on the previous slide. And now what we do is that we assign all 4 resistors R1, R2, R3 and R4 all to the same resistance value of R. And then we can eliminate this expression to the difference U2 minus U1. And that is exactly what we wanted from the beginning. So this circuit then can be used to measure the differential mode signal on a pair of wires. And as an alternative, I can say that if we assign R1 and R2 to the same value R, and then we assign R3 and R4 to K times R, then we will end up with an expression that has the output voltage of K times the difference of U2 and U1. So we can add also an amplification factor that is larger than 1. This has only the amplification of 1 equal to 1. So this is the difference amplifier, and the difference amplifier, as I said before, can be used to sense the differential mode signals that are stemming from a sensor. So it is an important amplifier for that purpose. And then an electromagnetic disturbance that creating an electrical field along the wires. Then if the wires are twisted and very close together, then we can assume that you have the same contribution from that electrical field on both wires, so it will create a common mode signal on this difference amplifier. If it is an ideal difference amplifier that only responds to the difference between those two terminals, then we can completely eliminate the disturbance that come from the environment. On the other hand, a real-world differential amplifier, and not an ideal one, will also respond to a common mode signal, this FCM, with a SCM, and the FCM is the amplification of the common mode signal, and the FDM is the amplification of the differential mode signal, that one that is desired and we want to have. And a quality measure then of a differential amplifier is its ability to suppress the common mode signals, and it is given by the common mode reaction ratio, CMRR, which is usually given in the decibel scale. So it is the differential mode amplification divided by the common mode differential amplification. And the 10th logarithm of this quote multiply with 20. So the relation between the differential mode amplification and the common mode amplification will give you a quality measure on how good this difference amplifier is at suppressing the common mode signal. An instrumentation amplifier is more or less the same as a difference amplifier, except that its input terminals has very high input impedance. And this high input impedance is achieved by a couple of additional transimpedance amplifier steps on the inputs. This can be seen here in this complete circuit diagram for an instrumentation amplifier, where we see a number of resistors and 3 different operational amplifiers. We will now continue to analyze this circuitry on the next couple of slides. And we can conclude that the last stage here seems to be the same as a difference amplifier in accordance to previous presentation, having all of its 4 resistors assigned to the same value of R. And the input terminal to this difference amplifier are the potentials UA and UB. And the input to the instrumentation amplifier, the whole circuitry, is U1 and U2. And these operational amplifiers are then used as transimpedance amplifiers, allowing for a very high input impedance on the terminals U1 and U2. Furthermore, we can conclude that the ideal operational amplifier model tell us that there is no current flowing into the terminals of these operational amplifiers, so that the current flowing through this branch must reasonably be the same as the current flowing through RF and RA. Equally, one can say that the input or the voltage drop over the input terminals must be equal to 0. And we can use these conclusions in order to develop a number of equations for this circuitry. UA, the potential on the input terminal here, must be equal then to U1, this input potential, plus the voltage drop over RA. And equally, UB is equal to U2 plus the voltage drop over this resistor RA. And then from these 2 equations we can develop an expression for UB minus UA, and that is equal then to U2 minus U1 minus 2 RAI. So we need to have an additional expression for I, and this we can develop from the fact that the potential on these terminals, this terminal and this terminal, must be equal to U1 and U2, since the voltage drop over the inputs to the operational amplifiers are equal to 0. This allows us to define the current is equal to U1 minus U2 and divided by this resistance RF. And now we can develop an expression for the output voltage as being the UB minus UA in accordance with what we developed earlier for this difference amplifier. And then we make a substitution for this expression using this expression and including also the current. And we will end up at this final expression for the amplification of the difference of U2 minus U1 on the input terminals. And the amplification factor then is according to this factor here, as we see here. We can continue with this result on the next slide. This is the same equation. And then we can compare this result with the data sheet of an instrumentation amplifier that is supplied by Analog Devices. It is referred to as AD620, and it has an additional connection for an external resistor, and this external resistor is RG, is the same as what we refer to as RF in our previous circuitry. So everything in this instrumentation amplifier, the resistors and the 3 operational amplifiers, are included into one single chip, except for this RF, here refers to as RG. And if you look at the gain expression that is also supplied in the data sheet from Analog Devices, it looks like 49 kilo ohms divided by RG plus 1. That then corresponds to this expression that we see here. And here is a schematic symbol having RG on the output. So this external resistor is then used to set the amplification of the instrumentation amplifier. Now, the main benefit of an instrumentation amplifier is its higher input impedance if compared then with a single operational circuit. This higher input impedance comes from the fact that the input signals are connected directly to the input of the close to ideal operational amplifiers. The 2 operational amplifiers that are part of this, that are making this trans-impedance amplifiers on the input of the instrumentation amplifier. The whole instrumentation amplifier, except the gain adjustment resistor, can be integrated on a single chip, and the amplification is then set externally by simply selecting a value for RF. The summing amplifier is interesting because of its ability to perform blending operations for blending of a number of signals into one single signal, or to perform a linear affine transformation of signals, as I will also show you later on. The summing amplifier is built from 1 operational amplifier and 3 resistors. It could even be more resistors depending on how many signals you want to add. But in this example we are adding 2 signals, U1 and U2, into one signal U out. And we will now perform circuit analysis to show you the mathematical development. And we can start with the Kirchhoff voltage law from this input U1 to the ground potential. So U1 minus the voltage drop over R2 is equal to 0, because that's where we end up at this virtual ground. The voltage drop over R2 is due to the current I2 flowing through R2, and I3 is flowing through R3, and then you have I1 flowing through R1, and later on we need to apply also Kirchhoff's current law on this node. But let's continue with the next step, which is the Kirchhoff's voltage law from this input node to the virtual ground. So U2 minus the voltage drop over resistor R3 is equal to 0. And we have been solving for the currents I2 and I3. We can continue with the last current voltage law from U out, and minus the voltage drop over R1, and again down to the potential of this virtual ground, and we solve for I1 in this case. And I think now we can continue with the voltage the Kirchhoff's current law on this node. And since we have been solving for I2, I3 and I1, then we can use the first equations 1, 2 and 3 and make a substitution into the fourth last equation. And then we end up at this result. And now we are supposed to rearrange this equation to solve for U out, which will have this result. And then we can see that the output signal is a summing of U1, Yeah, it's a linear combination of U1 and U2, and this linear combination, the factors are actually defined by R1, R2, and R1 and R3. So you can have different amplification factors for both of them. And then you need to add also the negative sign for the output, since the summing amplifier is based on a current feedback circuit. So this is our end result. And we can continue with an example on the next slide. And in this example, let's say that we have a sensor that gives an output that has a negative offset, a fixed negative offset, U off, and also it has a negative sensor coefficient, which means that with increasing physical property, the quantity that we are measuring, then we have a decreasing sensor voltage on the output. And we want to make a linear, affine transformation of the signal such that we can compensate and reduce this offset to zero and have a positive sensor coefficient such that the sensor output voltage will increase with increasing physical quantity that we sense. So we do this by adding a sensor signal on one of the input terminals to the summing amplifier, and on the other input terminal we add an offset, so such that we can compensate for the negative offset on the sensor output. So this is a sensor, the physical sensor output, and this is the output then after the summing amplifier. So we have made this linear transformation from this behavior and this dependency to this dependency, where we have a zero offset and we have a positive sensor coefficient. A charge amplifier has one single input, and this input behaves like a virtual ground, and any kind of current that we are from the external driving into this input will be accumulated into the amplifier, and it will be shown as a voltage on the output. So the time integral of the current will be shown as a voltage on the output. You see here on this picture we have a sensor that could be a piezoelectric crystal that is sensitive for applied forces, and the equivalent circuit for this piezoelectric crystal is the current generator, the resistance, and the capacitor. But now, since the input of this charge sensitive amplifier has an input that acts as a virtual ground, then the voltage over the input is equal to zero, and you have a zero potential on the input, and that will force all the current that is generated here in the sensor to actually flow into the input of the charge sensitive amplifier, and no charge will be accumulated in this capacitor, and no current will flow through this resistor, since the voltage over this resistor is equal to zero. So that is the basic idea, and all the current will then flow through this branch and will be accumulated into this charge. And this accumulated into this capacitor, and this capacitor then will give rise to a voltage that is reversely proportional to its capacitance, and you will have the corresponding voltage on the output, and the charge that is accumulated in this capacitor is the time integral of the current that is driven into the amplifier's input. We can continue on the next slide, and I have just given you here some examples and the circuit diagrams for two kind of mathematical functions in analog circuitry that was maybe more interesting in past. I'm talking about integration and also circuit for performing derivation. And the reason why it was more maybe interesting in the past is that these two circuits, they were used to solve differential equations by an analog machine. We were calling it like analog machines. So a network of this integration and derivations could be used to, for instance, simulate a process, industrial process, and the model of this process could be a higher order differential equation. Here for this integrating circuit, then the voltage on the input is shown as the time integral on the output, and the integration is performed by this capacitor. In the same way, we have a derivation circuit here, and the derivation is performed by this capacitor on the input. So the output is the time derivation of the input signal. This course, and I mean in particular maybe this presentation about operational amplifiers was most likely a review of knowledge that you already have gained in previous courses in analog electronics. But I have been trying my best to kind of put the analog circuitry into the context of measurement systems to give you more of a motivation why it is important and why you should also study analog electronics. So hang in there.